Okay, what we have to do in this exercise is you have a simple graph, right, which is G, and has n vertices, okay, and m edges. And this number of edges is bounded from below by this number here. So it is at least this number of edges, right? Which is pretty large, by the way. Well, we have to show that in this condition, then G must be a Hamiltonian graph. And the way to do this, I mean, we have very few results that with which to prove that some graph is Hamiltonian. And actually, the most powerful one we have is Orr's theorem, right? And if you remember Orr's theorem, what it says is that if you pick any two vertices which are not connected, right, in the graph G, and the sum of the degrees is at least n, okay, then if we have this situation for every pair of not connected graphs, not connected vertices, then G is Hamiltonian. Okay, so that's the result that we're going to apply in order to see this. Well, we're going to think of the graph G as the graph Kn, so the complete graph, in which we removing k edges until we get the number of edges that the graph has, right? Or until we construct the graph G. Okay, so for instance, suppose that you have 4 nodes here, okay, right? These 4 nodes, and these 4 edges, and they form the graph G, right? So you can think of this as constructed from the complete graph K4, right? In which you remove these 2 red links or red edges, okay? So you can always think of a graph this way, of a simple graph, right? As the complete graph in which you remove a certain number, well, some edges until you construct, or you're left with the graph G. So we're going to think of this graph this way, right? Okay, we know that this graph has n edges, right? So how many edges we have to remove from Kn in order to get this one? Well, the total number of edges of this complete graph is this. So we have to subtract m, right, which is the total number of edges of the graph G, and that would be k, the total number of edges that we have to remove. Okay, so, well, this is this number, but we don't know m, but we know a lower bound of m, right? So if we replace m here, so instead of subtracting m, we subtract this lower bound, what we have is an upper bound for the number k. So what we have is that this is smaller than or equal to this number minus this number here, which is n minus 1, n minus 2, divided by 2, minus 2. Okay, now you see n minus 1/2 is a common factor, right? And it's a common factor of n, and here n minus 2, right? And then we have minus 2 here. All right, n minus 2 is of course 2, so this cancels with this, and what we have is n minus 1 here, and here we have minus 2, so what we have is n minus 3. So in other words, the total number of edges removed is at most n minus 3. So this condition here translates into this condition here. All right? Okay. Now pick U and V, which are 2 nodes of G, which are not connected. Okay? Now we have to see if these verify the conditions of Orr's theorem. Right? That's what we have to do. Knowing this, right? So what we have to do is to estimate how much is this, right? This sum here. Okay. Well, they are not connected. So one of the links that we have to remove from the graph Kn in order to get G is the link that connects U and W, right? So at most, these two nodes have degree n minus 2. Remember, the node of any complete graph has, actually the node of any graph is limited, is bounded from above by n minus 1, because n minus 1 is the total number of other vertices in the complete graph. So if it is connected to all of them, then it will have degree n minus 1. So any vertex of any graph, any simple graph, will contain at most this number of, this degree, right? This number of edges. Okay, so they are bounded like this. But we know for sure that one of the removed edges is precisely the edge that we have removed from U and W, right? So this translates into n minus 2, right? So this bound that we have here. Okay, so this can be connected at most to any other edge, any other vertex except W, and vice versa, right? So both of them are at most n minus 2. And this is when one of the links that we are removing is precisely the link joining U and W. All right? Okay, so what is the worst case scenario for this? So when is this sum the smallest possible? Well, it would be the smallest possible if all the links that we are removing are removed either from node U or from node W. That's the way in which this sum can decrease the most, right? Okay, what would happen in this case? So this, what we are going to do is to obtain a lower bound for this sum, right? First of all, if we remove we remove the first edge, and the first edge removed is the one that connects U and W. So the total number of, after removing this link, the total number, well, the degree of these two nodes is, well, n minus 2 each, right? So the total number of, well, the sum of these two degrees is, to begin with, 2n minus 2. But now we have to subtract the remaining links from either U or W, which means that we have to subtract from this sum the k minus 1 remaining edges. Okay? Right. Okay. K minus 1, well, k is smaller than or equal to n minus 3. So k minus 1 is smaller than or equal to n minus 4. So if we put here, if we replace k minus 1 by an upper bound, and it's subtracting, then what we have is a lower bound. So this is larger than or equal to 2n minus 2 minus n minus 4. Okay? And now we can expand this. We have 2n minus 4 minus n plus 4. Okay? Simplify the 4. And this is n. So what have we found? We have found that the lowest possible value this sum can take, the lowest possible value it can take, so it can be bigger than that, but the smallest possible value is precisely n. And that is what Euler's theorem says. If this is true for every pair of vertices of the graph G which are not connected, and we have taken two arbitrary nodes which are not connected, then the graph is Hamiltonian. So this is the proof.